Hey, this is Mr. Adler, and this lesson is on radioactivity and half-life. I'm putting this lesson together because after knowing that students have been taught about radioactivity and half-life in earth science, in chemistry, and in physics, maybe even back in middle school too, it's bothering me that some students still are not completely getting this idea, and I want to show you another way, maybe a better way, to help you understand what half-life is all about. It's too important to stay confused about it because we use radioactivity and our understanding of radioactivity, including half-life, in so many ways. In earth science, we talked about how we can figure out how old rocks, woolly mammoths, fossils, things like that are. We use radioactivity in nuclear medicine to help see inside your guts without cutting you open, burning out cancer in people. It's very useful. And in everyday life too. If you have a smoke detector at home, which you do, you're using radioactivity to keep our house safe, your house safe. Things that are radioactive aren't stable. They don't stay the same material forever. An example that you saw back in earth science that we talk about a lot because it's in you, but don't worry because it's not dangerous, is carbon-14. Let's say you have a pile of radioactive carbon-14. It probably doesn't look like this, but it's giving off beta radiation. That's electrons being emitted from the nucleus of the carbon-14 atom. When that happens, the carbon-14 doesn't stay carbon-14. So it's emitting out of its nucleus. That's kind of interesting. Maybe you want to ask your teacher about that. It's emitting electrons from its nucleus. When that happens, it doesn't stay carbon-14. It converts into stable, non-radioactive nitrogen-14. As time goes by, you'll have less of what we call parent material, in this case the carbon-14, and more daughter material, the nitrogen-14. It does this at a regular rate. So as time goes by, what's going to happen to this pile is that less and less of it's going to stay carbon-14, and more of it is going to convert into nitrogen-14. Not right down the middle. But as time goes by, the percent of carbon-14 is going to go down, the percent of nitrogen-14 is going to go up. It does this at a regular rate. I want to show you what regular rate means, what radioactive decay means. Let's say you're looking at some radioactive material here. I'm going to start a stopwatch as I talk about this in a couple seconds. I'm going to tell you why later. Hopefully you've counted by now, and you see that we have 16 radioactive atoms for this example. There's typically many more. In truth, if you only had 16 radioactive atoms, you wouldn't be worrying about its half-life, its radioactivity, because it wouldn't be very much. But in any case, they don't stay radioactive. After a little while, maybe this one converts into a stable atom. Then maybe this one converts into a stable atom. Then this one. And so on, for a while. Okay, I'm going to stop my stopwatch. That took about 30 seconds. I stopped my stopwatch right then because if you look, half of the radioactive material has mellowed out. It's turned into stable atoms. The time it takes for half the radioactive material you have to disintegrate and change into stable material, that time's called the half-life. It's different for all radioactive materials. For the example I used in the beginning, carbon-14, the half-life is 5,730 years. Yeah, we know what that precisely. If you have a pile of radioactive carbon-14 and you could stand around for 5,730 years and look again, only half that pile would still be carbon-14. The other half would have converted to nitrogen. And it's like a clock, because that half-life, that time, it's constant. The remaining half of the pile, here's the tricky part, the remaining half of the pile you had would get cut half again in another 5,730 years. So you'd have 1/4 of the original radioactive material remaining. half of a half. And that amount, that 1/4 of the original, would get cut in half again 5,730 years later. That means 1/8 of the original would still remain. That's not the only time for half-life. Some crazy things at the high end of the periodic table have half-lives of milliseconds, microseconds. That's why you don't find them around very much around nature, because they don't exist anymore. They've changed. Other materials like uranium have half-lives of billions of years, and we can use half-life to help us figure out many different things, like how long something's been buried in the ground, how much stuff is going to be left after a certain period of time. So let's take a look at a couple of examples. I'll read this to you. Hopefully you can read it too. A 96-gram sample of radioactive material is placed in a container. After 12 minutes, only 6 grams of the sample has not yet decayed. What's the half-life of the radioactive material? Feel free to pause this video right now. See if you can figure this out by yourself. That'd be great. And that's the beauty of these flipped lessons on video. Give it a try. Take a moment to think about it. I don't know if you're watching it with friends. Talk. Hit play if you think you've got it or if you need help. Yay, flipped lessons. Every time you have this kind of problem, any kind of radioactive problem, you just want to keep thinking about cutting numbers in half. I want to assure you that since you're beginners at this, the numbers will always be easy to cut in half in order to get to our answers. In this case, you started with 96 grams of the stuff. I'm not going to draw blobs this time. I'm going to draw nice rectangle boxes. 96 grams of the stuff. We know that 12 minutes later, only 6 grams is still radioactive. You got to read the directions carefully. The next example is going to be a little bit more confusing. This question says you have 6 grams that are still radioactive, that has not decayed. Not decayed. My big hint to you is find out how many times you have to cut your starting number in half until you get to your final amount. How many times do we have to cut 96 in half to get it down to 6 grams? Well, let's cut it. If you can't do it in your head, write it out. If you can do it in your head, awesome. Either one of those is a fine way to get to your answer. What's half of 96? That's 48. Okay? So if one half-life went by, one half-life, we'd have 48 grams of stuff left. Okay? One half-life, you have 1/2 of what you originally started with. Obviously, we only have 6 grams at the end, so another half-life, more half-lives have to go by. If a second half-life goes by, how much are you going to have left? 24 grams. Hopefully we can cut 48 in half again. Still not there yet. Okay? But let's look at a couple things. We got 2 half-lives going by to get us from 96 down to 24. That means we've cut 96 in half and then in half again to give us 1/4 of what we have left. Couple of similar, couple of related ideas together. But we're still not there yet. If a third half-life went by, we'd have 12 grams. That's 1/8 of the original material, if you keep a track. Okay? Starting to look like we're getting close here. After the fourth half-life, we're going to have only 6 grams of radioactive material left. Okay? 1/16 the original amount. Not that that's part of this question's answer, but we're getting there. Okay? The 6 grams isn't the answer yet either. But we just figured out that it took 4 half-lives to get down to 6 grams remaining. We want to know what time it is for just one half-life. It took us 12 minutes, and we figured out that it was 4 half-lives. So here's the math. 12 minutes for 4 half-lives. This is the math that's going to tell us 3 minutes half-life. That's our answer, because it's always going to be the same amount of time per half-life. So here we go. We just figured out how long it takes for a half-life to go by for this material. We don't know what it is. That's not what this question was really about. Don't worry about that for right now. We always want to figure out how much time it takes for the material to get cut in half. We can do it this way, or we can try another example and see if this makes sense. Read it carefully. It's not worded the exact same way. A medical lab has a 16-gram sample of a radioactive isotope. After 6 hours, it is found that 12 grams of the sample have decayed. Confusing? Giving you a little bit of a hint here. What is the half-life of the isotope? Again, pause the video if you think you got this. That'd be great. Help out a friend. Okay? If you read it too fast, and you shouldn't have done that because you're way too smart for that, you might want to go, wait, I can't cut 16 grams in half and get to 12. But that's not what you have to do. So that's some good news. Don't do that. I shouldn't have even said that because it's the wrong thing. It says 12 grams of the sample have decayed. So how much is left? So in your head, you got to look at this. You go, 4 grams is left. 16 minus the 12 that have decayed equals 4. Okay? 16 grams is what we started with. 12 grams have decayed. So we have 4 grams left. You can do that in your head, but maybe it would just help to write it out. How much do I have left? Hopefully, you're going to get a little better at this, so that when it comes time to think, okay, how many times do I have to cut 16 in half to get down to 4? Won't be too bad. Okay? Start off with 16 grams. After 1 half-life, what would you have? 8 grams. After what you started with, just writing that because it's in my head. I don't want 8 grams left, I want 4 grams left. And hopefully you can see that you only need to go through 1 more half-life for a total of 2 to get down to 4 grams, which as a fraction is 1/4 of the original. So again, the math is how much time did it take for 1 half-life? 6 hours went by in our story. Don't read that question once, go back to it a few times. And we figured out that 2 half-lives went by in those 6 hours. 6 hours for 2 half-lives. That means it's 3 hours per half-life. The time for a half-life is what we're looking for. 3 hours. Hopefully, this is making a little bit more sense. Another way to look at this, we're getting near the end. Thanks for listening. Another way you might see this kind of stuff is on a graph. Should make sense. As more and more time goes by, you're going to have less material. You can see time on the x-axis. I left the y-axis blank in terms of numbers because there's a couple different ways we can view how much material we have left. I should write the word material. How much stuff we have. Before we talk about this graph, specifically about radioactivity and half-life, let's just review what type of graph this is. This is a very typical graph of radioactive decay. Time is increasing, material is decreasing. Parent material. What's the relationship? As time goes up, the amount of material goes down. That's an inverse relationship. Now I'm writing this just because different schools, different classes call this different things. It's also called an indirect relationship. And from what I hear in math class, they call it a negative correlation. Hope I spelled that right. Just trying to remember some stuff here. It should also make sense to you that if the radioactivity is changing, there's going to be less as time goes by. Now, like I said, I left the x-axis blank. That's because there's a couple of different ways the material can be represented. It could be represented as mass, something like this, 4 grams. And a question might be, if you had a graph like this, what's the half-life of the material? The graph makes it kind of nice to figure this out. You started out with 4 grams. That's the beginning of our graph. After 1 half-life, how much would you have left? Well, let's do this first. You had 4 grams. It's right at the beginning of our graph. After 1 half-life went by, how much material would you have left? If you started with 4, you would only have 2 left after 1 half-life. So you come across from the 2, and then you look down. How long did it take for our 4 grams to get cut down to 2 grams? Well, from here to here, that's 2 minutes. That's how long it took. That's our half-life. We can even double check if you're not sure. If you're wondering, did I do this right? It's almost too easy. Start with the 2 grams. After a half-life went by, how much would you have then? Well, then you'd only have 1 gram. I can do this. It's not a perfect graph, but how long did it take? Oh, from the 2 to the 4, that's 2 minutes. It should be 2 minutes because half-life's constant. It's constant in this case every 2 minutes. It took 2 minutes to go from 4 grams to 2 grams. It should, if I drew my graph really well, and real questions will be drawn very nice, 2 grams to 1 gram took another 2 minutes. Half-life is constant. That's the great thing about radioactivity. There's another way to do this. Then we're going to be done for this lesson. Instead of giving the material in grams, could be given as percents. Whatever the amount is that you start with, you consider it as 100%. Okay? Let me clear my stuff here. And let's look at it in a similar way. Doesn't matter whether it was 4 grams, 4 tons, 4 ounces. The original amount can be considered 100%. Then the graph would look like this instead. After 1 half-life, how much is left? Half. Well, that's the same as 50%. Same process. 100%. How long did it take to go to 50%? 2 minutes. Okay? There's our 2-minute gap. Okay? And again, we can double check. If we started at 50%, cut that in half, what's half of 50%? 25%. How long did it take? There's that pretty darn close to 4-minute mark. That's another 2 minutes have gone by. That's really important. It doesn't matter if the radioactive material is in the desert or on a mountain or underwater. Its half-life will always be the same for that material. If you're thinking about how well you can cut numbers in half, you should be able to figure out these problems without too much stress. And don't forget, there's always a teacher in class. There's nothing that says you can't watch this video a couple times, hit pause when you get to the tough spots. Hopefully all these things are going to help you to understand this idea of half-life and radioactive decay. It's something that you need to know because you deal with it all the time. I hope this helped. Thanks.